So, hello together to the statistics course. Today we will deal with some general types of distributions. We have talked about probability, we have talked about conditional probability, in general about the axioms of statistics, and now as a revision we will just talk about the main distributions we also will use further on in this lecture. And there we start with a classical distribution when we are flipping a coin, and this is a so-called binomial distribution. What does it mean, a binomial distribution? We have a random experiment, and especially in this random experiment we have only two possible outcomes: success or failure, or if you are flipping coins, this is the classical experiment for a binomial distributions. And then we are flipping the coin n times in a row, or we are doing the same experiment n times in a row, because if you make the coin flip, then of course, if it is a fair coin, we would say that the probability of the two possible outcomes will be the same, will be 50%. In general, we say we have two outcomes and maybe one outcome has a probability 20% and the other outcome has a probability 80%. So then we ask, what is the probability that if we are flipping our coin, or if we are doing our experiment n times, what is the probability that we have k times a success of the event within n times doing our experiment? Of course, we say that flipping the coin the first time, the second time, the third time, and so on, that all these events are independent from each other. And this we have learned in the last lectures, then we just can multiply the probabilities within our repetition, our experiment. And of course, I already said, this is not only an experiment with 50-50 outcome, but also 20-80 or 10-90 outcomes. So success has the probability p, and the failure has the probability 1 minus p. And then I think you already have seen this. We need the so-called binomial coefficients. These binomial coefficients you also know from the Pascalian triangle. If you take these numbers 1, 4, 6, 4, 1, 1, 10, 1, 5, 10, 10, 5, 1, then all these are the binomial coefficients. Oh, sorry, this is not really working. And this is one possibility to construct them, but we can also, if you doing something with, if you are counting permutations, then you know that n over k is defined as n faculty over k faculty times n minus k faculty. All of you know what is meant by faculty. So let's say, as an example, what did we do? 7 over 3 equals 7 faculty over 3 faculty n minus 7 minus 3 faculty. How do we calculate this? What is n faculty? This is just a shortcut for 1 times 2 times 3 times 4 and so on times n. So in this case we have 1 times 2 times 7 over 1 times 2 times 3 times 1 times 2 times 3 times 4. Then we can of course here 3 and the 4 also, and then we have 5, 6, 7 over 1, 2, 3 means this, and this is 35. And this just means that we have if we take 7 elements as a whole, and then we ask how many permutations do we have out of 7 elements to have a 3-element subset, then this means that there are 35 possibilities. But I think this you really have seen in your first statistic course, or? Hopefully. Okay, but if we take all this together, then we can show that the probability we ask for in the binomial distribution, what is the probability to be k times successful within n repetitions, means that this probability can be calculated by, n over k times the probability to be successful times the probability to be not successful. And if we take this together, then we can also show that the expected value is just n times the probability to be successful, and the variance is n times the probability to be successful times the probability to be not successful. And if we take this together, then we can really ask for some simple experiments when we take such binomial distributions, and in this case we can then calculate the probabilities. So we will do for some examples some simple questions. At first, probability within 10th rows of a dice to obtain 3 times a 6. What is the probability? What can we do then? Well, we just take our formula n over k. I think I can just copy it. Yep. And then put it in. What is n? If we take our question. Oh. So we wait again. Please come back. Yeah. What is n in the first question? N3 and K6? Just think about it. Within 10 throws, 3 times a 6. What are the events? The event is throwing a 6. And we ask for being 3 times successful. So we have n is our 10 throws, and k is 3 times to be successful, is 3. And what is p? If you have a fair dice, rolling a dice. What is yes? Not 1 to the power of 3, but the probability to roll a 6 is just only 1 over 6. And then we just put it in. We have 10 over 3 times 1 over 6 to the power of 3 times 5 over 6 to the power of 7. And in order to calculate, we just go again to Excel. You can also, of course, put it in your calculator. Let's take this one. Then what do we need? We need, here we can also say that this is 1 times 5 to the power of 7 over 6 to the power of 10 times 10 over 3. Oop. So we have then here is 6 to the power of 10, and we have 5 to the power of 7, and I think we have here binomial coefficients. I can't find them. So then let's say faculty of 10, faculty of what do we need? 3, and faculty of 7. Then we need is this over this times this. this is our binomial coefficient. So we have 120 possibilities. What is one possibility? The first possibility is, of course, in the first 3 rows we roll a 6, or another possibility is to roll a 6 when at event 8, 9, 10, or at event 2, 5, 7. All these are the possibilities. And all in all, we have here 120, and then we have to calculate is this over this times 120, and we end up with roughly 15.5%. But I think such a calculation you already have seen in your basics statistic course. So we have, I think, one exchange student here. I hope that I translate it in the right way. We have in Germany, we have a really famous game, and this means Mensch, ärgere dich nicht. I found it that it is called in Spanish, Hombre, no te enfades. I don't know if this is right. And within this game, you have 4 guys, and they are living in their house. And if they want to come out, you can roll the dice. And if you have a 6, then you can put one of your guys out of your house. And that you really start, because the probability is only 1 over 6. So roughly 16% to leave your house. It's not correct. Okay. So maybe you can correct me. If you find it, then just send it me how it is correct, how we can correctly translate it. So the internet is not always correct. We see here. But thank you. But I think everybody knows what we want to do, because then you are allowed not only to roll 1 time the dice, but you can roll it 3 times. And the question is, what is the probability that if you are allowed to roll your dice 3 times, that you have within these possibly 3 rows a 6? What do you think? Again, in statistics, to roll 1 time, a 6 is 16%, so it should be more. Do you think it is 20, 30, 80%? What do you think? Just make a guess. Okay, then we will have a look. How can we calculate it? So we start. And there, in this case, you often take the pattern of a game tree that we start. We have 2 possibilities, binomial distributions, so we start with our dice. And if we have our 6, probability 1 over 6, but it is also probable that we don't have rolled a 6. So with probability 5 over 6, we will roll again our dice. So here the tree stops at this 6, but here if we don't have a 6, then we go on rolling. And again, 5 over 6, 1 over 6, we stop if we have a 6, and if we don't have a 6, again, we are rolling our 5/6, 1/6. And here we also would have a 6. And then we just have to sum up all these probabilities. The first event is 1/6. The second possibility to have a 6 is this part of the tree, so plus 5/6 times 1/6. Remember, we can just multiply these probabilities because our events rolling the dice the first time and rolling the dice the second time are independent. And plus 5/6 squared, because this one, first, we don't have a 6, second time rolled, and the third time, again, 1/6. And if we sum up these probabilities, we come to roughly 42%. And that this is almost 50%, this is quite often a bit astonishing in this case, because mostly the people would guess that the probability is around 20 or 30%. Though again, this is some example where the result, if you are calculating then probabilities, if you're doing statistics, you have a surprising result in this case. Okay, then the last question here for the binomial distribution. We play 4 different statistically independent lotteries, and the probability of success is always 20%. First question, what is the expected value and what is the variance and standard deviation? Maybe we can, oops. $16, I think this is enough, and then I have some space left for the last question. So, A. Again, we need to know N and P. What is N and P? N is 4, okay, and P? Yes, 2/10. And then we have expected value is N times P is 8/10, 0.8. The variance is N, P, N minus P. So we have 4 times 2/10 times 8/10 is 0.64. And then the standard deviation is square root of 0.64 is 0.08. Then, really hard to calculate what is the expected payoff if every success counts 10 euros. There we can use the property of the expected value operator, that this is linear. So e of 10 times x is just 10 times e of x. So we obtain 8 euros, if you want to say. So then see, what is the probability to win exactly 2 times? Hmm? Yeah, again, we take our formula here. K is 2. So we have 4 over 2 times 0.2 squared times 0.8 squared. So we have 1 times 3, 4 over 2, 1, 2. And this is then 4 squared over 100 and 4, not 4, not 4 squared. Where we are, there, there. Over 100, and this, did I calculate this before? This is roughly 50%. And D, calculate the probability that you lose at least 3 times. This means we calculate the probability that we lose 3 times, and we also have to calculate the probability that we are losing 4 times, because at least means that we have to count the possibilities of the losing 3 times and losing 4 times. And for this, we just can switch around the probability here. If we are asking for the probability to lose, then we just put in for P 0.8. So this means switch to P equals 0.8. Then we have 4 over 3 times 0.8, 3, 0.2 plus 4 over 4 times 0.8. 4 times 0.2 to the 0, and this means a probability of roughly 0.81% if I have calculated in the right way. Okay, so I just save my file. And we will see later on that we have to use the binomial distribution when we are doing hypothesis testing. So maybe take your basics course out and you have also just a short look what was the binomial distribution. So, but we had it the last time. We have discrete distributions, but also, of course, we have continuous distributions, and now we will switch to these continuous distributions. So we now do not ask what is the probability of one specific event, but what is the probability of the realization of our random variable to be within specific area. And this just means that we have to calculate the area below our density function. So the probability that x is within the interval a and b is the integral from a to b over our density function. So if we have maybe fx such a density function, and this is a and this is a, then this would be the probability that x is element of a. B. This is in the first part abstract, but we will just in a minute do also an example. But again, the single value of f of x we cannot interpret as a probability. This is really important that you don't do this, because we have infinite, not countable, infinite numbers of events, so to speak. And this means that if we look at only one point, then the probability of every single event in a continuous distribution is just 0. But the other way around, of course, the integral over our total sample space, this has to be equal to 1 or to be 100%. If we sum up all possible events, so to speak, all possible realizations of our random variable to be within one interval, if we sum all this up, then we have to end up, of course, with 100%, and this means that the integral equals to 1. So we try to to do this at an example. Say student Mike is always late in the statistics lecture, and his delay is a continuous random variable with the following density function. What do we have to do if we want to calculate our density? Because our density is, at the first part here, indeterminate, because we have an external parameter a. What do we have to do if we want to calculate a? Well, just we go here and we take this property that our integral from 0 to 4, because here we have defined that our density should be 0 elsewhere, over a minus 1 over 8 times x dx. And what is the integral? Well, here we have a constant. If we integrate a constant, this just means that we have to calculate the integral ax, a, dx plus integral over 0 to 4 minus, sorry. Up. Minus 1 over 8 times x dx, and this is then ax from 0 to 4 minus, what is the integral over x? You need the second part. Hmm? So we just have to ask which function should we derive that we have 1 over 8 times x, and this just means 1 over 4 x squared from 0 to 4, and all this has to be 1, and then we obtain, I think a is 4 over 3 if I'm right. So we have 4a minus 1 over 4 times 4 squared is 1. So 4a minus 4 is 1. So we obtain, am I right? Hopefully. A is 5 over 4. I thought I had 4 over 3. Because I also wanted to show you the following thing, that we can, oops, where it is, no, we can again use some software tool, and this is, yeah, maybe the best mathematics tool in the world. Maybe you know the program Mathematica. Because of course we do not want to do all these little calculations, and therefore we just can, for example, put in that we formulate our problem, solve so this means to solve the following questions. Int means integral a minus 1 over 8 times x from 0 to 4 equals 1, and we have to solve for our variable a. Just put enter, and he is calculating, and we obtain a is 1/2. So somehow I should have made here a mistake. Where is my mistake? Oh, 1/4. Where is my mistake? Hmm. Here we have 1 x. Oh yeah, there's my mistake. It is not 1/4, but of course, if we derive it, we of course have to put the 2 in front, and this cancels then with 16 to 1/8. So here I also need to have 1/16, and then of course we have here the 1, and then we obtain the right result, 1/2. So then we can say that our density function is just f of x equals 1/2 minus 1/8 times x. How does it look like? Well, of course, for x is 0, we here at 1/2. And then we need also the cutting point with the x-axis. And this we just get if we set this to 0. So 1/2 equals 1/8 x. So x equals 4. So this is our density function, if we show it graphically. What else did I pose? Calculate the probability that Mike is between 1 and 2 minutes late at some specific day. Well, if we take this lateness, then we just put in here from 1 to 2, and this is then our lateness. And this, of course, we can calculate if we take the integral. So this is question 3, I think. Yeah. This is the integral of 1 to 2 of 1/2 minus 8 times x dx. So again, we obtain 1, 2 from 1 to 2 minus x squared over now the right one, 16 from 1 to 2, and here we need an x. This equals then 1 minus 1/2 minus large brackets 4/16 minus 1/16 is 1/2 minus 3/16, and then we have 8 minus 3/16 is 5/16. I hope that I'm right. So I also gave you here, if you want to try it, the possible formulas if you want just to calculate if you are doing some more than only plus, minus, and so on. You just can switch to this web page, Wolfram Alpha, and I would recommend that you just try it because this is really a helpful tool if you are doing some mathematical calculations. Oop. Here we are. I put it also in, and then you will get it. From my web page. So what else did I had? Sketch cumulative distribution. I think this we can leave out at this part. Cumulative distribution. This meant just that we have f of x is equals the integral of 1 to x f of y dy. This is also the same integration we already have done here. And what else? Expected value and variance. This would mean then just calculate. Yeah, maybe you can do it as homework. Integral over x, f of x, O to 4 dx, and variance of x is integral of x minus expected value of x squared f of x dx. Just put the numbers in and then you will find the right values. Okay, this was just one general example of a continuous distribution. A special continuous distribution which we quite often use is just the uniform distribution. Well, you will just get the formulas in this afternoon, or just wait. If you go back here, no, this was in the other. Sorry, this was in the other file. You have also these formulas in the old PowerPoint slides from the last week. There you have also seen this. But I just had to take the minute. Okay, thank you. But you will get it this afternoon or tomorrow. Okay, so uniform distribution. This means that if we look at this distribution here, then if we go from 2 to 3, then of course this area is larger than this area. But within the uniform distribution, there we say that every interval should have the same probability. And this just means if our interval has the length b over a, b minus a, then the height of our distribution function has to be just 1 over b minus a. So a uniform distribution just looks like this. And then, of course, if this is a constant here, then, of course, every interval with the same length has the same probability. And again, if you put this formula here and just say, okay, I want to again calculate e of x is integral of x f of x, then you end up very surprisingly in a uniform distribution with the other arithmetic mean of a and b. Well, if you think about it, then of course you will come to this result also if you don't do this integration here, that this has to be just the arithmetic mean of the limits of our interval. But if you then put in here the other formula, x minus e of x squared times f of x dx, then we end up with the variance. And if you do this, I think I will give you this also as a homework, then you end up with variance is 1 over 12 times b minus a squared. This, of course, then looks like this. This we already had. And if we go to the cumulative distribution, so of course, if I am always adding the same probability, because f of x is again integral of f of y dy, if in the same length we always add the same numbers, then of course we obtain for our cumulative distributions a linear function ending up, of course, at 1, because if we go up at the limit of our uniform distribution, then we are again at 100%, and therefore we have to have here the 1 in the cumulative distribution function. So also we do just a little example. Suppose you are the COP. This is something which I had in mind. So the chief of production. I don't know if the this really exists, but anyway, within a brewery. Furthermore, you are responsible for the filling machines, and there you have that the filling machines say always that you are filling 0.568 liters. Well, I took this number because this is just a pint in England, but you're knowing that not every bottle is filled with 0.568 liters, but that you have some error, and you are assuming that your your filling machine fills your bottles within a uniform distribution interval between 0.556 up to 0.58. And now we are asked, what is the probability that the filling quantity is less than 0.56 liters? At first, we need our density function. What do we have to calculate? Well, we just take the upper limit and the lower limit. So this would be 1 over 0.58 minus 0.556 times x, and 0.556 is lower equal x is lower equal 0.58, and of course 0 otherwise. And this means, hopefully I'm calculating right. You help me, please. Would then be 1 over 0.024. Am I right? Hopefully. But I think so. So how does it look like again? F of x is just 0.556 up to 0.58 and here 1 over 0.024. And what is the probability? Doesn't matter. I will also record it again and you can look it up maybe on the weekend. Bye. Okay, and then what is the probability less than 0.56? So we go in here, 0.56. So we have the probability is just this area here. And then we obtain, I think, 0. So P of x is lower than 0.56 liters is very surprisingly 0.004 divided by 0.024, and this is, I think, over 6. And 1 over 6 is pooh. This I have to calculate. Sorry. 16 of course. 16 period 6%. Well, of course, this also we can directly calculate since we say that from 0.556 to 0.56, this is just 1/6 length of our interval, then of course we have 1 over 6 as probability. But I think you should also try to really calculate it within our with our definitions, that you really practice it, because further on in this lecture we are always calculating expected values and some other things like that. Okay, this is our uniform distribution, and then we will start. I don't know if we will make it today, but we will start now with the maybe most important distribution we have in statistics, and this is a normal distribution. And the normal distribution is just written if you find the symbols here. So the n symbolizes the normal distribution, normally distributed with expected value mu and variance sigma squared. And the density function, well, this is really then some deeper statistics which we have, is given as 1 over square root of 2 pi times the variance times this exponential functions x to x minus mu squared over 2 times the variance. And of course, our normal distribution function looks like this. So this is just here our density function. But you have already seen, hopefully, the normal distribution. Yes, okay. So then, of course, this is a quite complicated function here. And if we want to calculate the cumulative distribution, then we have a problem because this integral does not exist with just an analytic version, and therefore we just we just write a new function which just symbolizes this not analytically to be solved integral, and this we call then the error function, where the error function is defined as in this way. So we have, so to speak, two possible ways to show our cumulative distribution, and I showed it here that if you take some statistics books, then maybe in one statistic books you find this version, and in the other statistic books you find this version, so that you are not be puzzled if you see here different things, because these things are of course both the same. So why is this normal distribution so important? This is therefore so important because really many empirical distributions follow at least approximately. So then if we don't know the distribution, then we very often make the guess that we say, well, let's try, and we suppose just that this is our random variable should be normally distributed, and then if we make our experiments, then we may quite often find that these distributions really follow at least approximately a normal distribution. And also we can say if we have some distribution, that if we have doing our experiments very often, that then the normal distributions approximate our specific distribution very good. And one version of this is the binomial distribution. So we really can say, if we don't want always to calculate these things we had in the beginning of this lecture today, then we also can say that if n is quite large, that we can really good approximate our binomial distribution with the normal distribution. And of course, maybe the most important reason is the so-called central limit theorem. We will talk about this later, and this means that we have some unknown distribution of our sample, and we don't know the true distribution. That if our sample is very large, so if we have 1,000, 10,000 events or so on, then we can say, because of the central limit theorem, that we can, the mean of our sample will follow approximately the normal distribution. And this is very often the question, what is the mean of our distribution? We, of course, know the sum will follow also our true distribution, but this we don't know. But from the central limit theorem, we know that we can approximately say, well, this mean will be, if our sample size is large enough, will follow the normal distribution. And of course, in the end, the normal distribution is quite often, very often, the basis for our theoretical models. If you say, then you have some external shock somewhere in your model, then you say quite often f of x plus some error term epsilon, and then we assume quite often that this error term is normally distributed, and if it is normally distributed, then we call this white noise. Often assumed to be normally distributed. And especially this property we will use also further on in this lecture. Okay, here again, how does it look like? This I already showed you. This is our density function. And if we calculate our cumulative distribution function, then of course we have to start at 0, and in the end we are reaching 100% here for the cumulative distribution function. So some properties of our normal distributions. Of course, this is a 2-parameter function. If we look it again up here, this is the one parameter, here's the parameter, and here you have the parameter, and x is our variable. It is, of course, this we use also quite often, a symmetric function. The symmetry just follows from this here. So x minus mu squared is, of course, a symmetric function. And then also we can say, if we look at our graph here, then we start here with turning to the left, and then at some point here we are turning to the right, and this turning point here, this we find to be is just mu plus sigma. So if we go here, if we go down here, then we can say that this point here is mu minus sigma, and these are the turning points. Is mu plus sigma. For sure, if we also look at the function here, if this goes up, the variance, then our density function will be flattened, flattened, and flattened. So we go then like this or like this if the variance becomes larger and larger and larger. And what else do we have? Of course, we have here, not like in our uniform distribution, there we just cut the x-axis. Here we are just reaching the x-axis asymptotically. So we really have also the very rare events in the end. They can also happen, but here they have probability 0. Okay. And then we have here the general normal distribution, where we have some general expected value and some general variance. And then we define the so-called standard normal distribution, and there we take just the expected value to be 0 and the variance to be 1, and this is then written as n of 0, 1. Of course, then if we put this in, this is 0, this is 1, the turning points at -1 and +1. And if we put 0 and 1 in our density function, then of course here our sigma is just 1. This cancels out, and here we also do not have again our sigma and mu, and we just have e to the power of -1/2 times x squared. And yeah, this function is really important in statistics because quite often we will transform, if we have a general normal distribution, we will transform our random variable to end up with a variable which is just standard normal distributed. And I think I have to look at the time. Should we do this today? Yeah, I think this we can also do today. So if we just take a random variable x, which is normally distributed, then we transform our x goes to that, and that will be x minus mu minus sigma, and we just put this in our general formula. Where do we have it? Here. If you put this here in your density function, then you will find very fast that this transformed variable will just be standard normally distributed. And this distribution is often called phi of z or phi of c. And since this is now symmetrically around 0, standard normal distribution, we would have that this area is just phi of c. Then, of course, if we take the whole area is just 1, then we can say that, let's take green, that the green part here has just the value 1 minus phi of c, and this is the property we have here. And Why do we do this? Well, quite often we just ask what is the probability that our random variable is smaller some specific value. Let's say smaller than 0.4. If we translate this, then with this transformation, we just put it in. From this, we just have x equals sigma z plus mu. This is this one. If we put this in, then this means probability that this term here is smaller than x. And within these brackets, we can again calculate that this is then sigma z smaller than x plus mu, or z smaller than x plus, minus mu over sigma, that z is smaller than this transformed number we have put in here, where I just said maybe smaller than 0.4. So, and why is this important? Because now we just can take again the standard normal distribution, and this standard normal distribution you find tabulated everywhere, you find in every calculation program and so on. And there you also can have then some specific numbers of this distribution functions here. And these we will use if we later on in this course we want to calculate, for example, some hypothesis that this is for a significance of 95% or something like this. Then we quite often use these distribution function. But now for today we have it, and the rest we will do next week. Hopefully I'm not ill next week, because maybe you have heard already that my son is positive tested. I don't know what will happen with me. Okay, also next week, because the university said next week is still online, so we will go on with online. You all know that Corona is coming back. In Germany, we have right now 300,000 new positive Corona tests at one day, the highest number we had during this pandemic. So I think we just have to wait if we can see in the lecture room, really. So we have to wait. So next week again online.